Welcome back to Physics 152 Online. Here's where we're going in the next part of the course in our discussion of wave motion. And we'll treat in one unit both the material dealing with waves on a string and then also sound waves. Now, we start off with some definitions. And a wave is defined as a propagating disturbance in a medium. We've just been discussing harmonic motion, which is the back and forth or periodic motion of a single object moving back and forth in a single direction. Imagine that you had lots of different masses connected to springs, and each of those masses are connected to each other with some tiny string or wire. Then if we moved one of them up and down, we would actually see that motion transferred to the object next to it. And so taken overall, that kind of system would make up a medium. All of those masses put together would make up a medium, and a wave would be a disturbance in that kind of medium that propagates. And there are two basic types. The first one we can imagine by envisioning a wave on a stretched string, like a guitar string. If you were to pluck that string, or if you were to grab one end of it and give it a shake, then you would see a wave pulse that would propagate from left to right according to the diagram. This is called a transverse wave because the disturbance in the medium, if we focus our attention on a single point on that string, that point would move up and down as the wave travels. And since those two directions are perpendicular, we call that a transverse wave. Transverse is just a different way of saying perpendicular. There's another possibility though, and this would be something that would happen in sound waves. Imagine a pipe with lots of air molecules inside that pipe, and if we put a speaker at one end of the pipe to generate a sound, what that would actually do would be to vibrate the air molecules and compress them a little bit closer together. And then that zone or region of compression would move through the pipe. So this region indicated by the dotted lines, the compression region, would move to the right. And if we focus on a single air molecule, its individual motion would be to the right and to the left, which is parallel to the direction of propagation of this wave. And so we call this a longitudinal wave because the disturbance, or the direction of motion of the medium, is along the direction of motion of the wave. So those two different types of wave, transverse and longitudinal waves, are distinct from one another, and yet they still share common properties. Mathematically, though, we would like to be able to describe the properties of a wave, and so we're going to introduce now the wave function, which is the mathematical way of describing the disturbance in a medium. And strictly speaking then, this equation that we write down here, y is some function of x and t, will be appropriate for a wave traveling in a single direction in space. And that's handy to think of the wave propagating on a string as a system that would have a wave function like this. So, for a wave pulse on a string that lies on the x-axis, what we are actually describing with this function is y represents the displacement of any particular point on the medium from equilibrium at a position x and at a time t. X represents the location of a point on the string, and t is the time. So f is simply some kind of function that would describe the shape of the wave pulse. It could be a sine, it could be a cosine, it could be some kind of a Gaussian function. Lots of different possibilities would all qualify as valid forms for a wave function. The general mathematical form for a wave that propagates, that moves through space, has to be like this. So whatever the function f is, the argument has to include x plus or minus some constant times the time. And that constant multiplying the time, we could show dimensionally, represents the speed of the wave. And the sign in here, the only difference that makes is if the wave is moving in the positive x direction, then you have a negative sign. If the wave is moving in the negative x direction, you have a positive sign. And I'll talk in class about why that happens to be the case. But that's just the rule that tells us, if we have a particular wave function, how we know which way the wave is moving. Now let's talk for a second about the speed of a wave on a string. And this is important because it turns out that the propagation speed of a wave depends on the properties of the medium. And for example, that wave on a string, if we have a stretched string like a guitar string, you probably know, if you've ever tuned a guitar, that one way of changing the properties of that wave is by changing the tension on the string. And it stands to reason that the higher the tension, the faster a wave could propagate along that string. And that's the case. But there's another property of the string that the wave speed depends on, and that has to do with how the mass of the string is distributed. So if you have a very, very thick string, then its mass per unit length along the string would be greater than if you had a very thin string. And so the two important properties of the string that will affect the velocity of the wave are the tension, F, and this mass per unit length. And the symbol we use for that is the Greek letter mu. Now what about a compression wave in a metal bar? In some ways, the metal bar is a lot like a stretched string, except that it's a three-dimensional quantity. And so there's something akin to the tension that describes the internal relationship of the atoms inside the metal bar, and that's something called the Young's modulus. It tells us basically how stiff the bar is. And then since the metal bar is a three-dimensional quantity, we wouldn't talk about mass per unit length, but rather its mass per unit volume. And that's given by the Greek letter rho. And finally, for the sound wave in air, the situation is very similar to the compression wave that you would get in a metal bar, except we use the term the bulk modulus to describe how closely the molecules in the air or another fluid interact with one another, how strongly they interact with one another. And so the bulk modulus B is playing the same role for a fluid as the Young's modulus in a solid. And again, it would depend on the mass per unit volume. So for the one-dimensional string, if we know that these two quantities are the only important properties of the medium that affect the wave velocity, we can look at the dimensions of those two quantities and the dimensions of v, which is what we're trying to find an expression for, and we can see how v depends on the tension, and that should be F rather than T, but how the velocity of the wave depends on the tension and the mass per unit length. So let's look at the dimensions for a second. All right, dimensions of tension are force, which is newtons, kilogram meter per second squared. The dimensions of the mass per unit length is just kilograms per meter. And so what we can see is these two quantities, we have to do something with them together so that whether we multiply them or divide them or raise them to a power, we have to end up with the correct units for just V, which of course is meters per second. So right away we can see that each of those two terms has kilograms, and the kilogram term has got to cancel out, right? If we multiplied these two things together, we'd end up with kilograms squared, and there's no kilograms in our final answer. So we know for sure that we must divide these two quantities. And so if we just, as an experiment, if we just took the tension F and divided by mu, the kilograms would cancel, and we would end up with meters squared over seconds squared. We want meters per second, right? So if we took the square root of F divided by mu, it would have the right units for a velocity. And so that gives us this dimensional result. Now this result that we got purely by considering dimensions doesn't tell us for sure whether there might be any numerical factors in this expression. So maybe there's a 2 outside, or maybe there's a 3 inside the square root. We can't tell that for sure from just this simple dimensional analysis, but we know that this proportionality must turn out to be correct. And so if you look at your textbook, there's a very careful derivation of what the wave velocity should be in a one-dimensional string, and it shows out that this equation is actually correct. So that's how the wave velocity depends on the properties of the string itself. Now let's shift our focus to get specific on a particular type of wave function. And a propagating disturbance that has a short duration we refer to as a wave pulse. It travels through the medium and then it stops. But if we take one end of our string and shake it up and down in a periodic way that repeats itself, it will generate a periodic wave. And so if the way we shake that is associated with simple harmonic motion, if the end of that string was connected to a vibrator that would shake it up and down in simple harmonic motion, then we would end up with a motion that would be a harmonic wave. And of course, that means it's going to be either a sine or a cosine function, or some combination of those. So the general equation of a harmonic wave on a string can be determined by plotting y as a function of x and t at various times. So on the next slide, let me show what that looks like. Okay, imagine that you have a string, and so here we're plotting the displacement y as a function of position on the string. And imagine that the left-hand end of the string is tied to some kind of vibrator that can shake it up and down. So you can see what this looks like. This pattern is a cosine function. And so at t equals 0, imagine that this is what the wave looks like at t equals 0. And of course, if we let it go to a later time, this pattern will be moving. And we're gonna write down an overall wave function for this harmonic wave in just a second. But at t equals 0, the shape of this cosine function is given by y equals a, the amplitude, times the cosine of 2 pi x over lambda. You can verify for yourself that this works, because of course, if x is equal to 0, cosine of 0 is 1, and y is just a. You can see that on the graph. And then if we shift over to one complete wavelength in space away from the origin, so if x is equal to lambda, then you get lambda over lambda, which is 1, cosine of 2 pi, which again is equal to 1, and that would represent a different place on the string over here. So if you move over one wavelength, then you come back to the maximum displacement, where y would be equal to a. So the wavelength, of course, is just the physical space or distance between two identical points on this wave. So what we have right here is the equation for the wave at time t equals 0. Well, how's that going to change if we want to take the time dependence into account? We already talked about how the general form for a traveling wave has to have y equal to some function of x plus or minus the velocity times the time. So here, let's write down the correct function for a wave traveling in the positive x direction, and that means it's got to have a negative sign in here. All right, so we can write down in our previous equation for what the wave shape looked like at t equals 0, we can take that equation and substitute the x with x minus vt, because we know that our general traveling wave has to have this form here. So what we had on the previous screen was y equals a cosine of 2 pi x over lambda. So the x we're replacing with x minus vt. And that is how we generate the general form for this traveling wave that shows us what its actual disturbance would be at not only all points in space, but at all different times. Okay, so if we simplify this, we're going to have 2 pi x over lambda inside the argument, and then 2 pi vt over lambda. So if we write it like this, we can now make a couple of identifications that will allow us to simplify this. We know already probably from a previous course or just from inspection, that the velocity of a wave is given by its frequency times its wavelength. Remember that frequency is 1 over the period. So this would say that the velocity is the wavelength divided by the wave period. And that makes sense, because the period is the time it takes for the wave to move so that it reaches an identical point in that time, right? So the wavelength divided by the period gives us what that speed is. Okay, so with this, we can now substitute in for v over lambda on the right-hand side. So v over lambda would just be f, right? That would give us y equals a cosine 2 pi over lambda x minus 2 pi ft, and we can remember from our previous study of harmonic motion that 2 pi f is equal to omega. All right, so now we have the general wave function written like this, and there's one more term that we're going to define. We're going to define something called the wave number, which is usually done just for convenience in mathematical descriptions of waves. So k, the wave number, is defined to be 2 pi over the wavelength, and it has these units radians per meter. So if we make that definition, then our final expression for the wave function is a cosine of kx minus omega t. The k was where we had the 2 pi over lambda previously. So there's a nice compact form. And one more thing that we'll do just to make this wave function as general as possible is to insert into the argument of the cosine function a phase constant phi, so that we get the most general form of this traveling wave. If phi is equal to 0, then we have a pure cosine function. If phi has some other value, then what we're really doing is combining a sine and a cosine function in a general fashion. So that's a compact way of writing down mathematically not only the shape of the wave at a particular time, but the shape of the wave at all times. And so remember, y is telling us the displacement of a particular point in the medium at position x at a time t. So one more thing that we'll just notice in closing is that when the wave function is written in this form, where the value of k and the value of omega are given, it's helpful to see that we can use our expression v equals f lambda, and of course f is omega over 2 pi. Lambda, from the definition of the wave number, is 2 pi over k, and when we multiply those out, we find the 2 pi's cancel, and we just get v equals to omega over k. So if you are given a wave function in the form shown here, and if you know what k is and you know what omega is, you can just divide those two in order to get the wave speed. So I hope this is a helpful introduction, and we'll do some examples in class. See you later.